Hey everybody, welcome back. Today we're going to talk about something called the binomial distribution. So just hold that in your, well, don't hold that in your mind. Just think about what I'm saying for now. We'll come back to that idea. I want to start by looking at something a little more familiar first. I've got two experiments written here. The first, rolling a three-sided die 3 times. And I defined a random variable x to be the number of 2s rolled in those 3 tries. And then we'll do this experiment where I've got some colored marbles in a bag. I'm going to pull 3 times with replacement, meaning each time I pull one out, I put it back in. So the same number of marbles are in each time. And I made a random variable y, that's the number of red pulled in 3 tries. So what I want to do is compute I want to build the probability distribution functions for each of these, okay? It's going to take a little bit of work. So first of all, I need the probability. Let's stick with this one for now. The probability of rolling no 3s. Okay. So how can I roll no 3s? It means I roll not a 3 first, not a 3 second, not a 3 third, right? So that's an and statement. Not a 3 and, not a 3 and, not a 3 on the second, on the third roll. Right, so we've looked at problems like this. I'm going to skip some details because this computation can be long. So what it means is I'm multiplying the probability of not rolling a 3 the first time. In other words, 2 out of 3 chances, right? There's 2 non-2 values, not rolling a 2, pardon me. There's 2 not 2 values the second time and 2 not 2 values the third time, right? So it's rolling a 1 or a 3, a 1 or a 3, a 1 or a 3. And we get 8 out of 27. The probability of x equals 1 gets a little more complicated. So I'm just going to talk through some of the details while I write down the computations here. Maybe I roll a 2 the first roll. That's a 1 out of 3 chance. And then I have to not roll a 2 again. Or I don't roll a 2 the first time, but I do roll 1 the second time and then not the third time. Or I don't roll a 2 the first 2 times, but then I do roll a 2 the last time. If you work this out, it comes out to 12 over 27, right? Just multiplying 4, 4, and 4 with 27s in the denominators. And then the probability that x equals 2, meaning I roll the number 2 twice. Well, that could be I roll it the first 2 times, but not the third. The first time, not the second, then the third time. Or not the first time, but the last 2 times. And this one works out to be 6 out of 27, right? There's 2 here, 2 here, 2 out of 27 here, 2 out of 27 here, 2 out of 27 here, total of 6 out of 27. And then finally, what's the probability of all 3 times rolling the number 2? Well, a third of a chance the first time times a third of the chance the second time times a third of the chance the last time. It's 1 out of 27. And so I've got my PDF. Okay. You can do a quick check. If you sum up those probabilities, each of them is between 0 and 1, and they add up to 1. Okay? All right. Let's do this again for this guy. Okay? Same idea. Remember, y is the number of reds pulled. There's 4 marbles in there, 4 colored marbles. So what's the probability I don't pull any reds? Well, I have to not pull it the first time, not the second, not the third. Right? And the chance of not pulling it the first time is 3 out of 4. Not pulling the second time is 3 out of 4. Not pulling the third time is 3 out of 4. 3 out of 4 times 3 out of 4 times 3 out of 4 gives me 27 out of 64. Then, probability that y equals 1 means pulling 1 red marble in all those tries, in 3 tries. So maybe I pull it the first time, but not the second 2 times, the next 2 times. Or maybe I don't pull it the first time, I do the second time, and then I don't again the third. Oops, that's a 4 right there. Or maybe I don't pull it out the first 2 times, but I manage to on the last try, And so I get 9 out of 64, 9 out of 64, 9 out of 64, or again, 27 out of 64. The probability that y equals 2, pulling 2 red marbles. So I could pull it the first 2 times, but not the third. I could pull it the first time, not the second, but then the third. Or I could not pull it the first time, then pull it the last 2 times. All right, what do we get? 3 out of 64, 3 out of 64, 3 out of 64, for a total of 9 out of 64. And then finally, the probability that I pull 3 red marbles means a 1 out of 4 chance on each pull. It's the only way to do it, and I get 1 out of 64. So let's put these in: 27 out of 64, 27 out of 64. Where did I go? 9 out of 64, 1 out of 64, right? So in this case, again, our probabilities are between 0 and 1, and if you add them up, you certainly get 1. All right, so the number one point I want to make, maybe not the number one point, but a big point I want to make, I think, is very obvious. That was tedious, right? This was a pretty ludicrous amount of things to go through, right? It was just a bunch of multiplications over and over and over again. We might notice something. There was a very clear pattern happening. I figured out these parts exactly the same each time. The probabilities were a bit different, right? But if you look closely at what I did, the patterns are very identical. It's not a sensible thing to say. Are very similar, right? The computations are very similar. So there's something to be noticed here. And it turns out that these two experiments fit into a category of experiments. And in fact, if I increase the number of marbles in here, or change the number of sides on the die, or how many times I rolled the die, or how many times I reached into the bag, we would still see similar patterns emerging, right? This is about as much as I want to do to demonstrate that. It gets pretty long. But once we know something's in a pattern, we can use that pattern to make it easier for us to work with. In this case, what that means is if we know an experiment is of a certain type, then the pattern is so well known, we will have it programmed into computers and calculators to use for us, and we don't have to go through all of this. So these two fall into a very particular kind of pattern, okay? So let's talk about what it is that's similar about them. Both experiments were what we call binomial experiments. Okay, so how do we know an experiment is a binomial experiment? Well, here were the key features to those two experiments that made them binomial. There was a fixed number of trials that we usually call n, okay? What we mean by that, right? If I do an experiment where I draw 10 cards, well, I only did the experiment once. Of course, there's a fixed number of trials. What we mean is if we repeat the experiment, we would have the same number of trials each time we did it, right? Experiments don't have to be set up that way. I could do an experiment with a coin where I flip it until I get heads, right? It's similar to the one I did, flipping it 3 times, but if I repeated it, it might not have the same number of trials, right? So we have to know that if we repeat the experiment, we'll get the same number of trials, right? Or in the bag one, I could say I keep pulling until I get 2 blues in a row, right? And that could take who knows how many number of trials until it happens, right? So we have to have a fixed number of trials. Both of those were. I was going to flip the coin 3 times. I was going to roll the dice 3 times, or pull a marble out of a bag 3 times, each time if I repeated the experiment, okay? Another key was that we divided our sample space, in other words, all of the outcomes, into success or failure. Okay, so I didn't use this language necessarily, but all we mean about success is the thing we're interested in. In the first experiment, that was rolling a 2. Okay, that was my success. Every other outcome, 1 or 3, was a failure. In the marble experiment, the success was pulling a red. Every other outcome, which was what, green, blue, or yellow, were considered a failure, right? I could have said, I could also do a similar one where I say, I'm rolling a 6-sided die, and success is the even numbers, rolling an even number. So then there's 2, 4, or 6, right? So a success could be any number of outcomes, and a failure could be any number of outcomes. But as long as those are set up so we divide the whole sample space into some event that we call success, some event that we call a failure. And we need to know that the probability of success is the same for each trial. And we usually call the probability of success failure. Sorry, P. We usually call the probability of success P. We call the probability of failure, we're going to call that Q, which is 1 minus P, right? And naturally, if the probability of success is fixed, the probability of failure has to be as well, because it's always going to be 1 minus P. So if that never changes, this can't change, okay? And then one more is that the trials are independent. Okay, so let's look back at the ones we just did. First of all, when we were rolling the die, the probability of success on each trial, rolling a 2 was 1 out of 3, and it was 1 out of 3 the first time, the second time, and the third time. And those trials were independent. It didn't matter what happened on the first roll, the second roll was going to have the same probability of success. We could also look at the other one, right? The same thing. We had a 1 out of 4 chance of pulling a red marble, and it was the same in each trial regardless of what we did the first time, because we were putting the marbles back in, right, with replacement. It seems like these two are the same, because we said when trials are independent, it doesn't change the probability of success knowing what happens on the first trial. However, it's not exactly the same. For instance, suppose I had an experiment where, let's think about that red marble experiment. I'm going to do the same experiment where I reach in and pull out a marble each time. However, each time I'm going to put back in the marble that I pulled out, and I'm also going to put in an additional red marble, right? The trials are still independent, because it doesn't matter what happened on the first trial. After the first trial, when I start the second trial, all 4 marbles are still going to be in there, plus an additional red one. So the probability is changed, but they are independent. Okay, it doesn't change what happened on the first one, but the probability is still changing. So we can't have that happening. We need to know that on each trial, the success is the same and that it is independent. Okay, so when we have an experiment like this, we can name a random variable in the following way. X equals the number of successes in n trials, right? Whatever that number of trials is. And if all of these things are true and we name a variable this way, right? Number of successes, then we say X follows the binomial. Let's say it this way, sorry. Let's say X follows a binomial distribution, right, with number of trials and probability of success P. Okay, here's the idea. This is the binomial distribution. If we have a binomial experiment, we name a variable this way, we know it follows this distribution. Remember what distributions are. They tell us about the probabilities of each value of our random variable. Because it's falling into a pattern, we can compute these very easily, and we have calculators and tables that do it for us, right? The computations look very much like those computations I did in those first 2 experiments. They're long and tedious, but they do the same thing every time. And so people notice that there's a lot of things that fall into this binomial experiment. Why don't we just come up with a formula? And there are formulas, you can look them up, but we don't even need to know them. They are, all we're going to need to know is how to identify that we're dealing with a binomial, and then we can use a calculator or a table. And typically it'll be calculators for us to compute them. Okay. All we need to know, what are the number of trials and what are the probability of success? Those are the 2 parameters, the two things we need to know which binomial distribution we're looking at. Right? If you remember stuff from algebra like lines, right? Lines come in the form y equals mx plus b. That's one way to write the equation of a line. Every line that's not vertical can be written in that form, right? They're all lines, but they're all a little different. They have different slopes, different intercepts, all that stuff. If you know m and b, then you know which line you're talking about. It's the same idea here. If we know these 2 things, we know what we're talking about. We sometimes use this notation. This sentence is long, so instead we sometimes write x, this little tilde, and this is just to say x follows the binomial distribution with n trials and p probability of success. Okay. We also get a couple of other things for free when we know this. Remember, we've computed expected value in the past. We have to multiply the value of our variable times the probability of that value and add them all up. Well, it turns out if we want to do that for a binomial random variable, the expected value, remember we also call it mu, is simply the number of trials times the probability of success. And in a similar way, we can compute the standard deviation for the distribution, and that's just n times p times q. Right? So we get a whole bunch of information for free if we recognize that something is a binomial experiment and name our variable so that we have a binomial distribution. Okay. All right. Let's do an example. We'll do a couple more examples to finish this off. So let's just look back at a very familiar experiment, our old standby, flip a coin 3 times. Okay, so, and we'll name x is the number of heads in 3 flips. Okay, so I claim x follows a binomial distribution with 3 trials and a probability of success 0.5. Let's confirm this, right? What do I need to know? Fixed number of trials. I'm flipping a coin 3 times. If I did the same experiments again, it would still be 3 times. We've divided the outcome into success or failure. I've called flipping a heads a success. Everything else, in this case, the other thing, tails, is a failure. Right? This is a good reminder too. Success and failure don't have to be good or bad. If you were testing a medicine, let's say a diagnostic treatment to determine if somebody had a disease, you might call finding the disease a success because you're trying to find it. Right? That's obviously not great for somebody to get the disease. Success is just the word we use. All right. Probability of success is the same for each trial. We always have a 50% chance of flipping heads, and the trials are independent. Our quarter doesn't remember what we flipped the last time, so the probability is unchanged by the previous flips. Okay, we have done this experiment enough that I think I can just write out our distribution without explanation. We've written out the sample space many, many times. This one is 1/8, 3/8, 3/8, 1/8, right? These are our probabilities of getting each of these values. I want to compute the expected value of x. Let's do it in 2 ways. Let's use the original formulation. I take the sum of each value of x times the probability of that value, right? Which in this case is 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. I get 0, 3/8, 6/8, 3/8, which is 12/8 or 1.5. Right? So the expected value is 1.5. However, I just told you when we have a binomial, I can just take the number of trials times the probability of success, which in this case is the number of trials is 3. The probability of success is 0.5, which gives us our 1.5. Okay, so that meets expectations. However, still not that great. This is an easy enough thing to do. It didn't save us that much. So let's change this experiment. Let's try a much more annoying experiment. Let's try the experiment flip a coin 30 times. Okay. And now let's have y equal the number of heads. And sometimes we just write this, okay? Whether we're talking about a binomial or not, I'm going to start using this notation sometimes. N is so commonly used with the number of trials. So unless there's some really big reason that it's going to be confusing, people will often just write this. So I'm saying the number of heads in 30 trials, okay, out of 30 trials, just to shorten this down, right? So for very similar reasons to last time, this follows a binomial distribution, except now we have 30 independent trials with a 50% chance of success, excuse me. Okay. Now, we can still figure out the expected value fairly easy, right? In this case, we get 30 times 0.5 or 15, which might not be surprising. We expect to get about half heads, right? However, computing our probabilities is going to be much more difficult, right? Making that huge PDF, figuring out the probability of let's say, flipping 7 heads, right? Well, you have to think about, okay, what's the probability of flipping it the first 7 times and then not flipping it the last few times, and then flipping it the first time and then the second time and up to the 6th time, then not the 7th time, but then flipping it the 8th time. And you can go through all these different combinations of ways in which you can flip heads and not flip heads, and you got to figure out how many combinations there are to work this whole problem out, right? It would get quite big. It would look very similar to this thing we did here, except the length would be massive, right? Each of these would have 30 computations in them, and it would get quite big. So we don't want to do that. So let's use technology to answer 2 questions. What is the probability of flipping 7 heads? And what is the probability? Let's answer 3 questions. Flipping 7 heads, flipping 7 or fewer heads, and flipping more than 7 heads. Let's answer these 3 questions, okay? So to do this, I'm going to turn to an online calculator. There are plenty of them out there. This is the one that I often use. Where'd you go? All right. So this is the one that I use. It's at StatTrek. They do a lot of good stat stuff there. So notice what we have here. This is their binomial calculator, binomial probability calculator. And notice what it asks for. Exactly the things we said we needed to know. The probability of success on a single trial, I've already put in 0.5. The number of trials is 30, okay? So we were asking questions about the number of successes, and I wanted to ask about 7. So I'm going to calculate, and we see all of our response, all of the values we need here, right? So let me just mark off the particular ones we wanted to compute. So we were interested in, second. Ah, there we go. Now it's working. All right, so remember we wanted to know the probability that x was equal to 7, the probability that x was less than or equal to 7, and the probability that x was greater than 7. So looking down here, right, the probability that x equals little x, we put in little x. So now all of these numbers, little x is 7, all of these values is 7. So this is the first answer we wanted. P of x equals 7. I'm going to write that down on our paper for when we go back. 0.001, I'll go 1896. And then we wanted less than or equal to 7. That one's right here. That one, 0.002611. And then greater than 7 lives right here. 0.997, let's go 7389. Okay, so that's exactly as simple as it is, right? We don't have to go through naming the events. Our job here is just to notice that the thing we're looking at is a binomial distribution. And once we know that, we can let the computer do all the work for us. The problems, like I said, start becoming excessively similar. And when mathematicians notice that they're doing the same thing over and over again, they decide to take shortcuts, write formulas, and those formulas can be programmed into computers, and they don't want to repeat the same work. We don't really like crunching numbers. We just like figuring out how it's possible to crunch them. Okay, so let's do one more example. Let's go back to the paper, do one more example. Okay, so before we do, I do want to note one thing, that if you look closely at these two numbers here, the probability of x equals less than 7, and the probability that x is, or sorry, y is greater than 7, those are the complements to each other, right? If our sample space, if I wrote our sample space, let's say I write it out by writing all the possible numbers of heads we could get, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I'll just write dot, 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 up to 28, 29, 30, right? These are all the possible numbers of heads we could get. Less than 7 or equal to 7 is all of these. Greater than 7 is all of these. In other words, this is y less than or equal to 7. These are the events y greater than 7, but this is just the same thing as y less than or equal to 7 complement, right? These two events are complements to each other. They're everything the other one isn't, okay? And we know when we have two complements, their probabilities always sum up to 1. Right, that was one of our rules from one of the earlier videos, that the sum of the probabilities of complements is always 1. Okay, so this isn't by accident, right? So if you're doing this, this is a good check to have, right? If things had rounded once in a while, because of rounding, you might get something a little funny. But in any event, there's an example of that happening again. Okay, actually, I'm going to skip the second example for now. We'll save that for a different video. This one's getting long enough, but I do want to share one other thing before we go, just to hint at something that's coming down the road. Let's take a look quickly at, so here's another thing I found online to illustrate a point. This is another site I like a lot, GeoGebra. I use them for graphing a lot, but I found they had this thing here. Let me explain what we're looking at. Let's make it a little bigger. Let's see, make sure I'm actually sharing that. Yeah, there we go. So what we're looking at here is a little animation, or I guess you don't call it an animation, but anyways, a little interactive animator that illustrates a binomial distribution. So notice up here at the top, where my mouse is, I can name the number of trials. So let's set it at n equals 1 right now. And here is the probability of success is 0.572, just kind of randomly. What we're looking at with these two bars, it looks a lot like a histogram, but instead of showing the numbers of times things will happen, it shows each outcome and how many, what likelihood that outcome is to happen. So right now, for instance, if we have a 57% or 0.572 probability of success, then the probability of having one success, notice the height is at 0.572. All right, let's write on here a little bit. Yeah, red's probably pretty good, right? So the height of this bar appears to be right at about 0.572, right? And then this is the probability of success, 0.4, right? What would that be? 0.428, right? Down here. So it's not a very interesting one, but it does look very much like a histogram. Let's increase the number of trials. Actually, let's clear what I've written because everything's going to go away in a second. Let's change the number of trials. So let's go to, I don't know, something like 10 trials. Let's notice what happens when I change the probability of success. The scales are changing because the heights change and they try to make it look nice at each height. So you can take a look at that. I'll just put something somewhat near the middle. Let's go up about here. Again, notice we've got, now it's a little more complicated. The probability is 0.612 for success out of 10 trials. So for instance, the height of this bar, the height of this tallest bar is showing me the probability of getting 6 out of 10 successes. It looks like it's up at about somewhere between 25 and 30%. It looks like just over 25%, right? So that's, I'm talking about this bar here. Its height is the probability of getting 6 successes, or the probability of getting 10 successes, right, is very low, as we expect. Even though we get success 0.612 the time, it's still hard to get 10 in a row, right? So it's visualizing these this distribution. So there is something else interesting that happens here, though. I'm going to increase my number of trials to play with. And there's a shape that might be noticeable to you as something we've only hinted at in the past and we are only hinting at now. But this binomial distribution, the way things lay out, looks very much like this bell-shaped curve. Or what we will learn to call the normal curve. And it turns out that, in fact, the binomial and the normal what we'll call the normal distribution down the road are very closely aligned to each other in certain conditions. And this is just hinting at that. So I just kind of wanted to lay that in there. We'll talk more about that in the future. For now, the most important points are making sure we understand what a binomial distribution is and how to recognize them. Right, that's what we need to be able to do at this moment. Just these, right? Understanding this, how this page works together, right? So that when you how to recognize you have a binomial experiment, how to name your variable properly in order to use it, and then the rest comes pretty easy, just plugging into some kind of either an online calculator, if you have a graphing calculator, they have this kind of stuff. Okay, that's all I'm going to say for now. Thanks, everybody. I'll see you next time.